Alright, so now we're going to apply the negative feedback concept to this high gain voltage controlled voltage source, and we're going to do this schematically. So here's our voltage source. We'll come out to our V out here. The voltage source puts out A sub V, or A for short, times VI, which I'm going to actually call this delta V, okay? So I'm going to use an input delta V. And what I really want to do is I want to amplify some input voltage VI. I'm trying to get this, what I'm after is V out, so what's desired is V out equal to 10 times VI. Okay, that's what I'm going for, but what I have is this AV that's between 10 to the 5 and 10 to the 6th. So clearly I can't just apply VI to my voltage controlled voltage source, because then I'd have VI times 10 to the 5 through 10 to the 6th, and that wouldn't achieve my goal of a gain of 10. So let me draw something here. We'll put our input voltage delta V like such. So this is the, if you will, I will kind of draw a box around this voltage controlled voltage source. Okay, and these are the terminals that I am the controlling voltage terminals. And how do I want to wire them up? Well, I want to feed VI into this amplifier path. Remember, what I have is I have AV, VO, I have this summer or difference block here, and I want to put VI in here, and I want to subtract some portion of the output. So this would be delta V, and so because I have the plus sign associated with VI, I'm going to feed VI into the plus side of this delta V, which means I have to bring the output, maybe I should have brought it around the bottom, but this will work, it just looks a little cluttered. I'm going to wire in V out this way. Okay, and if we do KVL around this loop, right, so we kind of come back around like this. If we do KVL, I can write this equation: minus VI plus, I follow it through, I enter the positive terminal of delta V, plus delta V plus VO is equal to 0. And what I have is, I have VO is equal to AV times delta V, or we could write, since I want to solve for VO and not delta V, ultimately, in this equation here, we'll write delta V is equal to 1 over AV times VO. And we'll plug that in over here. So we'll have minus VI plus 1 over AV VO plus VO is equal to 0. And we'll collect our VO term. And we can now write VO is equal to 1 over AV plus 1 VI, or we could write it as AV over 1 plus AV times VI. So VO, in the limit that AV goes to infinity, will tend toward, or in the limit it will equal 1 times VI. Okay, so I have this relationship here for any AV, and I have this relationship in the limit that AV goes to infinity. So I have partially achieved what I wanted. I do have a gain that is stable, that is independent of AV, as long as AV is very large, but I don't have a gain of 10, I have a gain of 1. And that comes back to this fact here that we are to send back just a portion of the output, not all of it. And what I have done in this wiring, this initial circuit, was to send all of the out back. So I need to make a little modification. All right. So for a gain other than 1, okay, a modification is needed, i.e. we need beta added to the circuit. So how can we do that? Well, I know how to, if beta is less than 1, right, so between 0 and 1, I know what kind of network will give me a voltage out that is a fraction of the voltage in. I just need a voltage divider. So that's what we will do here. So redraw this. Here's VO. And what I'm going to do is connect a voltage divider like this, R1, R2, and we'll do this. So this is delta V. Alright. So again, if we go around, if we do KVL around the loop, we have minus VI plus delta V plus whatever the voltage is here. I'll call this V feedback, okay, plus V feedback is equal to 0. Well, VI is equal to delta V, which is VI minus, wait a minute, what did I do? Oh, sorry. I want to express delta V in terms of V out, right? I'm solving for V out. So this is 1 over AV, V out, right, plus the feedback voltage is just the voltage division. It's R1 over R1 plus R2 times V out. So I'm going to solve for V out, and I can write V out is equal to 1 over AV plus R1 over R1 plus R2 times VI. Or we could write it as R1 plus R2. No, let's leave it as we'll write it as AV over 1 plus AV times R1 over R1 plus R2. And I can rewrite this as AV over 1 plus AV times beta, where I'm going to define beta as being equal to R1 over R1 plus R2. Now, in the limit that AV goes to infinity, VO will equal 1 over beta VI, which is equal to R1 plus R2 over R1 VI, or we could write it as 1 plus R2 over R1 times VI. And we now see that if R2 is equal to 9 times R1, I can achieve a V out that is equal to 10 times Vn. Alright, and I've achieved that with this ideally infinite gain voltage controlled voltage source and a resistor divider. I can redraw this, just kind of to close the loop back on the block diagram that we drew before. We can redraw as a block diagram. It's really a signal block diagram. And here we would have AV, we'd have V out, VI coming in, V feedback coming back, and beta here is R1 over R1 plus R2. So this is this is delta V. This is a block diagram representation of the circuit that we just explored. Well, now we're ready to introduce our op-amp. Okay, the ideal op-amp, operational amplifier. The operational amplifier is, in fact, at least in its ideal form, a voltage-controlled voltage source, just as we have looked at. And it has a positive terminal, call it V plus, and a negative terminal, V minus. These are two input terminals. The voltage across which we will define as delta V will show a resistance between the two inputs, and the output voltage that's produced is going to simply be some large gain AV times delta V, the difference between the positive and the negative input terminals. And we use a symbol of a triangle. Of course, this won't look very good here. I'll redraw this in a minute. Okay, and we simplify this. Well, the other thing that is included here, which we won't go into detail right now with, is that there are power supplies, at least the positive power supply, I'll say VCC. Sometimes there is a negative power supply, I'll call it V minus VEE. Sometimes it's just grounded. But you know enough already about amplifiers and how, in order to produce amplification, we need a power supply. You think of the the NMOS amplifier, right? You have a VI, you have a VO, but there is power. There's VCC coming in, and there's ground, right, down here. And so even though when we think of the signal path, we think, oh, we come in this end, and it comes out here, and we can kind of forget about VCC being part of it, but we know in the end that there has to be a power source to be able to achieve this kind of amplification. The same thing is true with the op-amp, and if we were to look under the hood, we would see that an op-amp is really produced by just a collection of mostly transistors, all powered by a positive VCC power supply, and oftentimes by a negative power supply, VEE, minus VEE. Although, again, like I said, sometimes it only requires a single supply. But we're going to forget about the power supplies and just focus kind of on the signal path now. So the ideal, or the symbol we will use for an op-amp is this, where we have negative supply, positive supply, an output, a positive input, and a negative input. And we even go further, oftentimes not even showing the power supplies. Again, this is because we're focused simply on the signal path. Of course, if you built this, you would have to have a power supply or it wouldn't work. This is analogous to when we draw an OR gate or an AND gate. You don't have to show the power supplies, but you know that in order for that to work, there has to be power to the IC. Okay, so let's draw the previous circuit. Draw the previous voltage-controlled voltage source circuit using the op-amp symbol. Okay. What we're going to find is that the circuit that we just came up with, that was, using this abstract high-gain voltage-controlled voltage source, is a real circuit that you can go in the lab and build, provided that you have an op-amp. So what we will have is our operational amplifier. We have VO, and we have our input signal VI, and it will go into this positive input. We have our voltage divider coming off of our output, R1, R2. This junction between here is V feedback, and we're going to take that and connect it back to our op-amp. Actually, I don't need that arrow. This is in the block diagram. And this is equivalent to what we drew previously. The voltage at the input is delta V, going positive to negative from the positive input V plus to the negative input V minus. Okay? And if we were to solve this, we would say, okay, VO is always equal to AV, that's the ideal gain of this op-amp, times delta V. You say, well, what's delta V? Well, delta V, so let's look at the circuit. Delta V, you could do KVL, around here. Certainly can do that, but we can do this by inspection. You say delta V is equal to, well, I see on the positive side of delta V is VI, and on the negative side, I have the output of this voltage divider, and that voltage divider is R1 over R1 plus R2, VO. And now all we need to do is to collect VO. So we'll have 1 plus AV times R1 over R1 plus R2 is equal to AV times VI, and we arrive at the same result that we had previously, which is this right here. So as before, and this is equal to R1 plus R2 over R1 VI in the limit that AV goes to infinity. Now, one of the wonderful things about op-amps is that we can simplify the analysis by assuming that the gain is infinite. All right? And that leads to some simple steps for solving amplifier op-amp circuits. So these are ideal simplifications, which are actually quite reasonable for many uses of op-amps. In other words, this is not just a theoretical exercise. It actually works this way in the lab. At least so until you are going in and you're measuring truly values to 0.001% or that kind of accuracy. Then you need to take in consideration the finite gain. But most of the time we're not needing to do that. So if AV is let's say essentially infinite, okay, then since delta V is equal to VO over AV, right, that's just a different expression, same thing as this guy here, but we're solving for delta V, then delta V has to be equal to 0, right, in the limit, since V out is going to have some finite range. In fact, although this circuit here that I just drew does not show any power supplies, and hence analyzing this circuit would not ever give you any indication of what kind of output voltage was achievable. For instance, if I picked R1 plus R2 to be 1,000 and R1 to be 1, then the gain on this amplifier would be 1,000 over 1, be a gain of 1,000. If I put in 1 volt, then this math here, or result here, tells me that the output would be 1,000 volts. possible. That's possible if you had a high voltage op amp that was powered off of some power supply rails that exceeded 1,000 volts. Right? But most of the time in the lab, you're going to be powered off of 10 volts or 5 volts, 15 volts, 3 volts, something like that. And so you have to keep that in mind, that although this ideal analysis would predict a higher voltage, you're not going to be able to achieve a voltage that goes beyond the rails. In fact, a lot of times you can only get within some fraction of a volt or a volt away from the rails. Right? So that's not stated here. I mean, we can leave that aside for a moment, but when you actually go design a circuit, you do have to consider the fact that your op amp just can't produce any arbitrary output voltage swing. It is limited by the power supply rails that are powering it. So, back to our ideal simplifications. If the gain is infinite, then because delta V equals V out over AV, and because V out is finite, that's what I was getting to when talking about the power supply rails. So, whether it's plus or minus 10 volts, plus or minus 100 volts, whatever those rails are, VO over AV, where AV is infinite, will give you a ratio of 0. So the first simplification is delta V, which is equal to V plus minus V minus, is equal to 0. All right, that's actually a rule that we don't go solve for that. We actually claim that right from the beginning. And then secondly, you notice that although I drew a resistor up here, I did not actually include any resistance here. And I should have stated that we assume that Ri is infinite. Okay, so if Ri is infinite, then I plus and I minus, in other words, the currents going into the plus and minus terminals, right, are going to be equal to 0. So our second rule is I plus equal I minus is equal to 0. Right? No current flowing into the input terminals and no voltage across the input terminals. This is predicated on having negative feedback. And this is one of the kind of tricky subtle points about op amps. It's not that the input terminals of the op amp are actually holding their potential to a 0-volt differential. They actually are high impedance. You look into them, there's infinite resistance. They accept or demand no current, and so they have no ability, the input terminals have no ability to actually affect the voltage that is applied to them. It's the architecture, the topology that you wire up using this op amp that ensures that. And the topology that is needed is a negative feedback topology. In other words, if the output voltage goes too high, the negative feedback tends to reduce the input voltage, which, when multiplied by this very large infinite gain, will reduce the output. If you had it the other way around, an output voltage that went too high produced an input delta V that actually increased, that's positive feedback, and you would never get to this point of regulation where delta V, or V plus minus V minus, is equal to 0. Okay, so that, I can't emphasize that enough, that negative feedback has to be present in order for these rules to apply. So now we'll apply these on another op amp circuit.